Okay, and next I'd like to introduce Jochen from the Max-Planck Institute. He's going to be talking about Skyhopper.
Good morning, everyone. I'm Greiner from Munich. First of all, thanks to the organizers, because I will not talk about the interplanetary project. Yet, I think also the normal groups have their challenges. And my hope is that you will find some of those interesting and you might get across them over the next years. So instead of talking about the solar system, let me take you to a little journey a little bit far away. I'm not talking even about the next stars, also not about the next galaxies. Let me talk about the very first stars which formed shortly after the Big Bang. And that's the ones which we want to look at with Skyhopper. You might realize that looking at the most distant objects in the universe is causing the troubles. It's those that so you all certainly have heard about the Big Bang. You certainly also have heard about the microwave backgrounds discovered 40 years ago. In terms of distance or age, the astronomers typically talk in terms of redshift, with a little c. So the microwave background originated at a redshift of 1000. We are now at redshift 0. There's a long period where nothing happened in the universe except for expansion. And then roughly at redshift 20 or so, the very first stars formed and the very first galaxies. And which one formed first? Let's see. And so that roughly corresponds to 10% of the age after the Big Bang. Now, looking at those stars is somewhat difficult. So you all know about JWST, which was rated in terms of projects and sensitivities. Had the idea to look at these first stars while they're still shining. It's now realized that these first stars are much fainter and JWST will not see them. On the other hand, these stars will explode at the end of their lifetime. And when they explode, 1% of those will produce a gamma ray burst. We don't really know how these bursts are produced, but if they are produced, these objects raise in luminosity by a factor of 1 million. And that's the time that we can look at them. And we can also find them with a 10 centimeter telescope. You don't need JWST for that. The point is, these things fade with time, and they fade rapidly. With a 10 centimeter telescope, you can see them for about 1 or 2 hours. With JWST, you can see them for a week. So the idea is, let's launch a CubeSat, find these things, and then tell JWST where it should look in the next few days. Now, I don't want to mention all these then follow-up interesting science questions which you can do once you measure these in a certain number. So let's just look at what these bursts will do. So as I said, these gamma ray bursts are related to the life of very massive stars. These massive stars live very short. We can detect them in gamma rays before the distance of the universe, but we can't measure the distance. And so apart from pinpointing these objects, the next question is to measure the distance. And then just pick those which are really very distant. And this is done by typically spectroscopy. So that's using the Doppler effect on the spectral lines in what the objects emit. And one example is shown here. So you have your your normal spectrum, say in the UV, and then the Lyman absorption basically drops out all the photons below a certain redshift. And that dropout will change with redshift. So imagine you have a spectrum, so this is intensity over wavelengths, energy, or frequency. We have a spectrum which is flat. And then at a certain redshift, the Lyman absorption will basically eat all your photons at below energies. Now, if you take the object to further distance, to larger redshifts, then this dropout will move to longer wavelengths. So I've indicated above here some photometric bands in the optical, UV, the near infrared, JHK. And so the idea is that if you measure your spectrum in a number of photometric bands simultaneously, then you can guess pretty accurately what the redshift is. So if I measure more or less the same intensity in all the 4 bands, then I know that the redshift is maybe 1 or at most 3 if they're right here. If I measure the similar flux only in 3 bands, and the short wavelength band is not out, so there's a large difference, much fainter in the short wavelength band. Then such a 5. But we can also measure something like this. And actually, we did this with a different instrument from the ground a couple of years ago. So the largest redshift burst which we have measured is redshift 9.4, and that looks similar to this one. For this, we use a 7-channel camera from the ground, which had 2 more optical channels. So these things exist. The question is, we want to see more of those. And that's us where Skyhopper comes in. The atmosphere on the Earth is our phone. So if we go above the Earth's atmosphere, then a 10 centimeter telescope will do the same thing as a 2 meter telescope does on the ground. And this is just because we are using the temperature of the atmosphere. So the near infrared at 1 to 1.7 micron, that's the sweet spot where you gain most with most cost. And that's, if you look at it, it's exactly those 2 bands today, right? Where we still reach redshifts of 12 or 13. So that's a basic idea in terms of science and what we want to measure. From that, we derive those requirements, what we need for the CubeSat to do. So first, we want the fast slewing to the new gamma ray burst before the afterglow fades within an hour or 2. So we get the position and the timing from the gamma ray satellite. That comes down to Earth within a fraction of a second. It also comes to my computer in a fraction of a second. And so we want to send it up to the Skyhopper within, say, 10 seconds. That's generous. And then this CubeSat should slew to that position, say, within 10 minutes. Next, we want to be very sensitive because these things, despite being a million times brighter than normal massive stars, are still pretty faint. So we are talking about 20th magnitudes. Next, we want to have superb imaging qualities at the diffraction limit in light, which is about 12 seconds. And so this is good for 2 things. First, it adds sensitivity because as we increase our goodness of max imaging quality, the sensitivity goes down. Second, we want to get JWST in the position. And so everyone here in the audience, I guess, will recognize that the 2 second is not so. Next, we want multi-band imaging because only then you can recognize the language of art. And last, we want to go up to the H-band in order to see the dropouts also for redshift up to roughly 13. So this is what we kind of came up with in some brainstorming over the last year. It's a 12-view system with an effective 15 centimeter telescope. Effective because we think we can do it. So we want to make it as big as possible, but we need to need some other things going into the volume. So we came up with a 10 by 20 centimeter mirror. Where I had a spacecraft with 3 degrees per second slew speed, high quality stability, 84 seconds, then 4 channels in the optical and near infrared. I'll show you more details about this in a second. And then the vector should be actively cooled, something like 140K, because, and the optics as well, because we have to collect background speed, thermal background of the CubeSats. And that's the sensitivity in terms of standard units for a candidate exposure at single okay, so this is the mission concept under development. Phase B is funded. Here I see Michele Trenti from the university. Now, the discovery bursts happen only once every 2 days. So we also invented some science which we do in between, and that's basically looking at exoplanets. Now, that's the other topic in astronomy these days. And in particular, you already heard about the SVOM system a couple of weeks ago. So that's exactly what we could also do with Skyhopper. The Skyhopper would be the Spitzer successor for exoplanets. We just look at systems where the one big planet has been found, and we stare at it and look for planets. Okay. I might jump over this because that just tells you about the sensitivity of our system. So this is memory afterglows, which we have seen over the last 10 years with the 2 meter telescope on the ground. And the Skyhopper limit is here, so we basically are sensitive to something like 90% of all softwares. Okay, so that's the distribution of units over the different systems. Now, they're from my kind of more astronomy-related background, 2 challenges. One is on the telescopes, and the other one is on the beam study. And so for the telescope, we developed a classical 3-mirror system, but including a code set to find all the thermal heat from the CubeSat. So we have to basically only cool everything which is behind the code set. That's a detector, that's a beam splitter, and so we have 3 mirrors after that, which it's a 2 meter focal length system. The problem with the telescope is the little mechanical tolerance. So because everything is so compact, the distances have to be accurate to go out of position like one. And that has also to be maintained for the different heat load due to the frequent frequency. So still we get close. So the nearly diffraction limit is a 2 by 2 pixel box. So for most of the field of view, it's roughly 1 degree diffraction limited. Beam splitting is the other interesting problem. So the classical ways of beam splitting, which I took from Wikipedia here, they all don't work because you basically split your wavelength bands into areas which you can't focus on one detector anymore. This is an example of a system which we built 50 years ago on the ground. So you see that how the detectors are spread over distances of 50, 60 centimeters. we had to come up with something else and ended up with what we call the Extra system. Its principle is taken from the ecosystems in the 60s. Combined large empires. And we just developed the same and add the force channel. So basically, you have your inputs, incoming beams, and then you have like for beam splitting flags at these locations. Get force channels. Talked already that needs also included. And this bottom is a simulation of the redshift 8 memory burst, where you see just the innermost 1 minute out of the 1500 field of view. You don't see anything in the shortest wavelength band because the London absorption is completely eaten the flux, and then you see the object. Depending on which area of bands you see it, you can actually determine the redshift accuracy of 10%. So that's about it. We usually, of course, available all the time. Data transfer is also a problem. The time, observing time will be distributed like this, so the slide stops. And this is my summary. Most of these are still wish lists, so you get there.
I think we have time for a question.
About the first localization, I guess is sort of related to how you download the data. Do you guys do any sort of onboard identification of the GRBs from the? So my question is actually related to how much initial localization you need in order to make your system work.
So the first detection, of course, comes from the gamma ray satellite. So that has a position accuracy of pure minute. That basically determines the size of our field of view that we cover that. So that's why we've chosen the 1 degree field of view. And then we should do the positioning, so finding the new object and the positioning on board to, say, 1 or 2 seconds. And that should be done on board, and only that new position should be transmitted to ground. So we don't have this methods to set up the building.
If I may follow up, so if let's say not Swift or some other GRB system is giving you like 5 or 10 arcminute localization, would that then be a problem for you guys? Or?
No. We have a field of view of 1 degree. Yeah. Basically, we cover the whole terra box of the cameras.
But I was wondering if you download all those images.
No. We do the onboard detection and localization on that.
Can you give more information on the cooler you're using?
It's an off-the-shelf quiet cooler. I can give it.
Any further questions? Okay, then let's thank our speaker again.